Hi everyone. The purpose of this video is to discuss a property, or shall we say two related properties of the Poisson process, which play an important role in the generalization of the process. We will come to know this important property as infinite divisibility, and we shall also find out that there is a natural connection between infinitely divisible distributions and Lévy processes. We shall also eventually find out that Poisson play a prominent role in the characterization of the Lévy process. The story in this video is very simple though. All we want to explain is that the Poisson process is closed under superposition and decomposition, meaning that if you merge independent Poisson processes, you get a Poisson process. And if you split a Poisson process according to some random probability, then the resulting processes are also Poisson processes. And if one can carry out this split for any positive integer, then one is dealing with infinitely divisible distribution. This explanation will come in handy one day when we discuss general Lévy processes. Let's start with the merger or superposition. Consider a time interval from 0 to t, and let's say we have m Poisson processes, with intensity lambda 1, lambda 2, and so on, until lambda m. These could be representing the arrival of people with different hair colour, say blue, green, red, etc. Let's represent the number of arrivals over the interval by capital N. So N1 represents the number of arrivals of the first process over the interval from 0 to t, and so on for N2, all the way to Nm. Assume someone is monitoring the arrivals through a black and white telly, so they are not differentiating the hair colours, and they will thus only get the total count across the individual processes. If this person is also a fan of the Poisson process, then the good news is that the merged process will also be a Poisson process. Easy way to show this is via the generating function, which is like the power series representation of a sequence, or probability density in our case. It is similar in spirit to the Fourier series, or characteristic function, which applies more generally in both discrete and continuous situations. But the generating function is only for the discrete case, though much simpler to understand and appreciate. The reason one uses generating function or characteristic function when dealing with the sum of independent variables is because the characteristic function of the sum is equal to the product of the individual characteristic functions. So derivations are much easier. Let's write the generating function of the merged Poisson process. So this is just the expected value of the random variable raised to the power of a variable. This is similar to moment generating function or characteristic function, but we have simple power function in the place of an exponential. Now, the expected value of a function of a random variable is simply equal to the function value weighted by the probability. Where we substitute the density of the Poisson process that we have covered in detail before, we can move the exponential outside the summation and combine s with the lambda and t. Let's zoom in to see the details. Now, this sum is just a power series representation of exponential. So we can replace the summation by the exponential, and then combine the terms in the exponent. And we get the probability generating function of a Poisson process. So the probability generating function for each of our processes will have this form, but with different lambdas. Now, we know that n is the sum of the m ni's. So in the generating function, we can replace n by the sum of the components. As the n's are independent, which simply represents the product of the probability generating function. Each of the probability generating functions will equal this expression, but with different lambdas. And let's zoom in case the terms in the exponents are not clear. And we can combine the terms in the exponent and write the exponents in terms of the summation. And as t and s don't depend on the index, we can take them out of the summation. We can now replace the terms in the exponent, and we get the generating function of a Poisson process with parameter equal to the sum of the m lambdas. So we conclude that when you have m independent Poisson processes, then the superposition of these processes produce a Poisson process, which intensity is simply the sum of the intensities of the component processes. In terms of examples, the need for superposition of processes can arise in several situations of practical interest. For example, in a call center situation, we can talk about merging the arrival of calls at several call centers. Another example, one can view the radioactive emission process as a superposition of emissions from separate atoms. Now let's go the opposite direction. Assume we have a Poisson process, and we split the arrivals into m streams according to some probabilities. These could be splitting the arriving people by hair colour if you like. So the sum of these probabilities is equal to 1. And this splits or decomposes n into m ni's. Now, given n total arrival in the interval, we can write the conditional probabilities of this split using multinomial density. So this is a multivariate version of the binomial density. Instead of 2 outcomes, head or tail, we have m outcomes. Now, we can get rid of the conditional on n by multiplying through by the probability of n, which is just the Poisson density, because n is a Poisson process. We can cancel n's, and we know n is equal to the sum of m components of n. So we replace the n in the exponent by the sum. And as the sum of pi's is 1, we can also insert the sum of pi's into the exponent. This is like multiplication by 1, which changes nothing, but will help us decompose the formula. It is easy to see that we can write it as a product of m terms. For example, let's extract the terms containing the first component. We can do the same for the second, and so on, until the mth component. So we see that the formula actually represents the product of m such terms, and we can write it using the product symbol as follows. We can combine the pk and lambda times t terms and call it lambda k. And making the replacement, we get the product of m Poisson densities with parameters pk times lambda. So we have shown that we can decompose a Poisson process into multiple Poisson processes. And we recognize that this is very much the definition of an infinitely divisible distribution. Remember, we said that the concept of infinite divisibility is similar to the central limit theorem, but much easier to understand. A random variable, say n, is infinitely divisible if for every positive integer, say m, there exists a sequence of independently and identically distributed random variables, which we represent by ni's, such that n is equal in distribution to the sum of these variables. And we know analysing the sum of random variables is much easier when we use characteristic function. Just drawing your attention here, because we will be saying the characteristic function a lot in this series. So we can say the distribution of Poisson process has this infinite divisibility property. And we will find out later in this series that there is a close connection between infinitely divisible distributions and Lévy processes. So everything is going to come together eventually. This decomposition magic is also behind what is called thinning. So assume you have a Poisson process, but you lose or discard observations randomly with some probability p, which could be for all sorts of reasons, such as error in detection or for pure sampling purposes. Then we can see that the retained observations will also make a Poisson process, but a thinned version of the original process, with intensity proportional to 1 minus p. And you can easily see why it carries the name thinning. We hope you enjoyed the video and look forward to seeing you in the next.